1895 to 1937, early nuclear science. November 8, 1895, German physicist Wilhelm Conrad Röntgen discovers X-rays. 1896, French physicist Henri Becquerel discovers radioactivity. 1898, Marie and Pierre Curie discover polonium and radium. 1911, Ernest Rutherford articulates his model of the atom, at the center of which exists a nucleus containing the majority of the atom's mass and all of its positive charge. Ernest Rutherford, June 3, 1920. Ernest Rutherford speculates on the possible existence and properties of the neutron in his second Beckerian lecture, London. Irene Joliot-Curie, December 28, 1931. Irene Joliot-Curie reports studying penetrating particles produced by beryllium when bombarded by alpha rays. She believes the particles, which are actually neutrons, to be energetic gamma rays. May 1932, British physicist James Chadwick discovers the neutron. Leo Szilard. Photo courtesy of Argonne National Laboratory. September 12, 1933. Leo Szilard conceives the idea of using a chain reaction of neutron collisions with atomic nuclei to release energy. He also considers the possibility of using this to make bombs. This predates the discovery of fission by more than 6 years. Irene Joliot-Curie and Frederick Joliot in their laboratory. Photo courtesy Association Curie-Joliot-Curie. Mid-January, 1934, Irene Joliot-Curie and Frederick Joliot conduct the first demonstration of artificial radioactivity. Enrico Fermi. May 1934, Enrico Fermi and his team in Rome bombard elements with neutrons and split uranium but do not realize it. Leo Szilard. Photo courtesy of Argonne National Laboratory. July 4, 1934, Szilard files a patent application describing the use of neutron-induced chain reactions to create explosions and the concept of the critical mass. Ida Noddick. September 1934, Ida Noddick publishes a paper in Zeitschrift für Angewandte Chemie arguing that the anomalous radioactivities produced by neutron bombardment of uranium may be due to the atom splitting into smaller pieces. October 22, 1934, Enrico Fermi discovers the principle of neutron moderation, and the enhanced capture of slow neutrons. October 8, 1935, the British War Office rejects Leo Szilard's offer to turn over to them his patents of nuclear energy for free, an offer made to bring them under British secrecy laws. James Chadwick. December 1935, James Chadwick wins the Nobel Prize in Physics for discovery of the neutron. February 1936, the British Admiralty accepts Leo Szilard's offer to turn over his patents. 1938 to 1939, discovering fission. J. Robert Oppenheimer. January 29, 1939. J. Robert Oppenheimer hears about the discovery of fission. Within a few minutes, he realizes that excess neutrons must be emitted, and that it might be possible to build a bomb. Otto Hahn. December 21, 1938, Otto Hahn submits a paper to Naturwissenschaften conclusively showing the production of radioactive barium from neutron-irradiated uranium. A reconstruction of Otto Hahn and Fritz Strassmann's nuclear fission experiment. December 24, 1938, Otto Frisch and his aunt Lise Meitner correctly interpret Hahn's results as evidence that the uranium nucleus had split in two. Fission. Mid-January 1939, Leo Szilard hears about the discovery of fission from Eugene Wigner. He immediately realizes that the fission fragments, due to their lower atomic weights, would have excess neutrons that must be shed. Otto Frisch. January 13, 1939, Otto Frisch observes fission directly by detecting fission fragments in an ionization chamber. With the assistance of William Arnold, he coins the term fission. January 26, 1939, Niels Bohr publicly announces the discovery of fission at an annual theoretical physics conference at George Washington University in Washington, D.C. The Carnegie Atomic Physics Laboratory. January 28, 1939, physicists recreate fission experiment at the Carnegie Atomic Physics Observatory in Washington, D.C. Niels Bohr. February 5, 1939, Niels Bohr realizes that uranium-235 and uranium-238 must have different fission properties. Uranium-238 could undergo fission by fast neutrons but not slow ones, and that uranium-235 accounted for observed slow fission in uranium. Enrico Fermi. March 1939, Enrico Fermi and Herbert Anderson find that there are about 2 neutrons produced for every 1 consumed in fission. April 22, 1939, Frederick Joliot and his group publish their work on the secondary neutrons released in nuclear fission. This demonstrates that a chain reaction is indeed possible. June 1939 Enrico Fermi and Leo Szilard submit a paper to Physical Review describing subcritical neutron multiplication in a lattice of uranium oxide in water, but it is clear that natural uranium and water cannot make a self-sustaining reaction. July 3, 1939 Leo Szilard writes to Fermi describing the idea of using a uranium lattice in carbon, graphite, to create a chain reaction. Albert Einstein and Leo Szilard working on the famous letter August 2, 1939 Pray. Roosevelt receives the Einstein letter, warning about the prospect of an atomic bomb. John Wheeler August 31, 1939 Niels Bohr and John A. Wheeler publish a theoretical analysis of fission. This theory implies that uranium-235 is more fissile than U-238, and that the isotope of the undiscovered element 94 with 239 nucleons is also very fissile. These implications are not immediately recognized. The New York Times front page on September 1, 1939 September 1, 1939 Nazi Germany invades Poland, beginning World War II. 1939 to 1941 Investigating nuclear weapons. October 21, 1939 The first meeting of the Advisory Committee on Uranium in Washington, D.C., which was created at President Roosevelt's order. The physicists argue for urgent government attention, but Adamson is hostile. Teller requests $6,000 for research on preliminary uranium graphite slow neutron experiments, which is grudgingly approved. Rudolf Peierls February 1940 Otto Frisch and Rudolf Peierls, living in the United Kingdom, consider the possibility of fast fission in uranium-235. Based on a theoretical estimate of the fast fission cross-section, they estimate the critical mass of pure uranium-235 at a pound or 2, and that a large percentage could be fissioned before explosive disassembly. They also estimate the likely effects of the bomb, and possible assembly methods, as well as estimates of the feasibility of isotope separation. March, 1940 After much prodding by Leo Szilard, Lyman Briggs, head of the Uranium Committee, finally releases a promised $6,000 budgeted for conducting neutron experiments with Enrico Fermi at Columbia University. A billet of uranium. March, 1940 Otto Frisch and Rudolf Peierls conclude that only 1 pound of highly enriched uranium is needed for a bomb. John Dunning March 2, 1940 The first direct measurements of the enormous slow fission cross-section of uranium-235 are made by John Dunning at Manhattan, NY. The New York Times front page on April 9, 1940 April 9, 1940 Germany invades Denmark and Norway. Henry Tizard April 10, 1940 First meeting of the British Committee, later code-named the Maud Committee, organized by Henry Tizard to consider Britain's actions regarding the uranium problem. Research into isotope separation and fast fission is agreed upon. Lyman Briggs April 27, 1940 Second meeting of Lyman Briggs the Uranium Committee. Briggs' decision is that neither research on fast fission, nor work on building a critical uranium graphite assembly, should begin until the small-scale lab experiments, just getting underway, are finished. George Kistiakowsky May 1940 George Kistiakowsky suggests gaseous diffusion as a possible means for producing uranium-235 to Vannevar Bush during a meeting at Carnegie Institution. May 10, 1940 Germany launches its assault on Western Europe, attacking Holland, Belgium and France. A plutonium pellet. May 27, 1940 Louis Turner mails Leo Szilard a manuscript arguing that the isotope of element 94 with 239 nucleons, not yet discovered, should be highly fissionable like uranium-235, and could be manufactured by bombarding uranium-238 with neutrons, to form uranium-239. The same day, Edwin Macmillan and Philip Abelson submit the report, Radioactive Element 93, to Physical Review describing the discovery of element 93, neptunium, produced by bombarding uranium with neutrons. Britain subsequently protests the publication as a violation of wartime secrecy. A diagram of the gaseous diffusion method for separating isotopes. June 1940 The Maud Committee acquires its name. Franz Simon begins research on isotope separation through gaseous diffusion. June 27, 1940 The National Defense Research Committee (NDRC) is created to organize U.S. scientific resources for war, including research on the atom and the fission of uranium. Vannevar Bush and Arthur Compton July 1, 1940 The newly founded the National Defense Research Committee, headed by Vannevar Bush, takes over responsibility for uranium research. In his final report, Lyman Briggs requests $140,000 for further work, $40,000 for lab measurements, and $100,000 for large-scale uranium graphite studies. Bush approves only $40,000. Harold Urey November 1940 John Dunning and Nobel Prize winner Harold Urey begin investigating isotope separation techniques without U.S. government support. November 1, 1940 The $40,000 contract from the NDRC finally comes through. Work begins at Manhattan, NY to assemble a large subcritical pile made of graphite and uranium oxide. December 1940 The Maud Committee issues a report on isotope separation authored by Franz Simon. The report concludes that manufacturing uranium-235 by gaseous diffusion is feasible on a scale suitable for weapons production. Philip Abelson February 1941 Philip Abelson begins working on uranium enrichment at the Naval Research Laboratory. He selects liquid thermal diffusion as the technique to pursue. February 24, 1941 Glenn Seaborg and his research team discover plutonium. Lyman Briggs March 1941 The Department of Terrestrial Magnetism (DTM) at the Carnegie Institution measures the fast cross-section of uranium-235. Using it, Rudolf Peierls, on the Maud Committee, calculates a new critical mass for uranium-235 at 18 pounds as a bare sphere or 9 to 10 pounds when surrounded by a reflector. A memorandum is prepared by the Maud Committee describing the importance of fast fission for bomb design and transmits it to the U.S. Briggs locks up the document on arrival and shows it to no one. Glenn Seaborg and Edwin McMillan March 6, 1941 Glenn Seaborg and Art Weil isolate the first pure neptunium-239 0.25 micrograms. In a matter of days it decays into a barely visible speck of pure plutonium. Joseph W. Kennedy March 28, 1941 Joseph Kennedy, Glenn Seaborg and Emilio Segre show that the plutonium sample undergoes slow fission, which implies it is a potential bomb material. May 1941 After months of growing pressure from scientists in Britain and the US, particularly University of California at Berkeley's Ernest O. Lawrence, Vannevar Bush at the National Defense Research Committee decides to review the prospects of nuclear energy further and engages Arthur H. Compton and the National Academy of Sciences for the task. The report is issued May 17 and treats military prospects favorably for power production, but does not address the design or manufacture of a bomb in any detail. At this same time, Bush creates the larger and more powerful Office of Scientific Research and Development (OSRD), which is empowered to engage in large engineering projects in addition to research, and becomes its director. May 1941 Tokotaro Hagawara at the University of Kyoto delivers a speech in which he discusses the possibility of a fusion explosion being ignited by an atomic bomb, apparently the first such mention. Emilio Segre May 18, 1941 Emilio Segre and Glenn Seaborg determine that the slow cross-section of plutonium-239 is 170% of that of uranium-235, proving it to be an even better prospect for a nuclear explosive. June 22, 1941 Nazi Germany invades the Soviet Union. June 28, 1941 The Office of Scientific Research and Development (OSRD) is established. Vannevar Bush is put in charge. July 1941 Emilio Segre and Glenn Seaborg measure the fast fission cross-section of plutonium-239, finding a high value. The Maud Report July 15, 1941 The Maud Committee approves its final report and disbands. The report describes atomic bombs in some technical detail, provides specific proposals for developing them, and includes cost estimates. Although the contents of the Maud Report reach Vannevar Bush at the Office of Scientific Research and Development immediately, he decides to wait for the report to be transmitted officially before taking any further action on fission development. In short, the report concludes that an atomic bomb is indeed feasible. A sketch of the Chicago Pile 1 August to September, 1941 Enrico Fermi and his team at Manhattan, NY begin assembling a subcritical experimental pile containing 30 tons of graphite and 8 tons of uranium oxide. It gives a projected K value of 0.83, indicating that purer materials are needed. Edward Teller September, 1941 Enrico Fermi muses to Edward Teller whether a fission explosion could ignite a fusion reaction in deuterium. After some study, Teller concludes that it is impossible.